Does it match? Of course it matches. You just wrote it down. Oh. There's all my work. So what you're saying is all night when I felt guilty about not putting this online, no one cared because no one did it anyway. Oh, okay. All right. So Hunter asked, how can I just get rid of these and these, right? Okay. So first off, the 4 becomes 8 waters, and the 8 becomes 16 waters. And the way that I cancel those out is over here. Since to balance the charges, I had 5 electrons and 2. I had to multiply 5 by 2 and 2 by 5. So that's where these come from. When I right here, yes. So that's okay. The 8 waters and 16 hydrogens. Hold on. Right. So when you multiply this by 5, you ended up with 30 H plus on the left. Over here you had 16 H plus on the right. So you subtract the small from the big. So 30 minus 16 left 14 H pluses. The same thing was done with water. We had 8 H2Os over here, but over here we had 5 times 3, which was 15 waters. Those cancel out because you take the small number, subtract from the big, and you had 7 H2O left over on the right, so that's how it became right there. I was reducing them. Yeah. Right here. Okay, that's a really good question because this part can be very confusing. All of it can be, really. All right. This number right here is the oxidation number of Bi in BiO3 minus. But this number doesn't matter in the overall thing, and that's why this can be super confusing. Ignore the blue for right now, okay? So to balance this, I first had to balance the waters by adding 3. Or I had to balance the oxygen by adding 3 waters. Okay? Is this recording? Yeah. So I added 3 waters right here. Now, to balance the hydrogens, I had to put 3 times 2. So 6 H pluses over here. And now it was balanced, but I had to do the charge part. So I came up here. The only charges I account for are the ones it gave me in the problem. So the -1 and the +3. And then any that I added. Now I know that's confusing. I didn't add this charge because it wasn't really a charge. It was its oxidation number. And that's one of the gigantic landmines of these whole problems. So I knew this side's total charge was +3. I knew this charge's total side was 6 pluses minus 1. So it ended up being an overall +5. Now that is the same as this number, but that's just random. Okay? So I had to make +5 equal +3. So to do that, since it was a reduction, I gained electrons in the reactants. So I had to add 2. So now I have +5 minus 2 equals +3, and now the charges were equal. That makes sense? That is usually the #1 place kids screw up, because they have these oxidation numbers written, and it can really mess with your lives. Because this one, that's its charge and its oxidation number. So I do include that one. But the difference is this one, it told you it was a +3 to start with. All right, we found Mn and Bi. Okay, now back to step 1, unless anyone has a lower question, which is fine. Don't worry if you're step 1, because that's probably most people. Okay. Somehow pulling out that chair, and I just hurt my back. That really hurt. All right. So I have Mn, and it tells me it is a plus 2. That's what this means. So I have Mn plus 2, and then I'm going to go over here. Oxygen's going to stay the same unless it goes to an element. So I know that the two things that are going to change are Mn and Bi. So I'm going to put MnO4 over here, and it's a -1. Okay. Down here, I have BiO3, and it's a -1. And it will go to Bi plus 3. Okay, now, I can know that, but I also should know how to find these charges. So manganese, its charge will be assigned to it based on whatever oxygen tells it it has to be. Oxygen's the boss in these oxidation and reduction reactions. That's why they're called oxidation reactions. All right, so I take oxygen is always a -2. I take 4 and multiply it by -2 to get a -8. All of this adds up to equal -1. So manganese has to be something that when you subtract 8, it equals -1. So that means it's a plus 7. All right, so it went from a 2 to a 7, or became more positive. So yes, we would say this one was oxidized. If it becomes more positive, it lost electrons, and we lose electrons, we're oxidized. Post, you okay with that? Okay. Now, we know O is going to maintain the same, so it's the same idea. This one is nice because it already tells me Bi is plus 3. All right. This one, we just have to figure this out with the same logic. We have 3 times -2, so that's a -6. Something minus 6 equals -1, so that's a plus 5. Plus 5 to plus 3 means it became more negative or closer to negative, which means it was reduced. Fair enough? Okay. Now, I wrote these in black on purpose. Anyone know why? Because I'm not going to use them later. When we go to balance charges, these numbers are useful to figure this out, but they're not part of the balancing. Just the charges it gave me in the problem. Those are the ones that count. You want me to work through the whole thing again real quick? Okay, let me rearrange it. Okay, so first you would balance manganese, but it already is balanced. Next, you balance oxygen. To balance oxygen, we add what thing? Water. All right? So there are 4 oxygens, so I need 4 H2O. Are we okay with that? Okay. Then, what's the next step? Balance H's. I now have 8 H pluses. So I need to add 8 H plus. Are we okay with that? Okay. Now, I have everything's balanced except for the charges. I have a total of -1 plus 8 on this side. Is everyone okay with that? So technically over here I have a plus 7 overall. Is that acceptable? Okay. And by the way, I erased it, but was this one the oxidation or the reduction? This was the ox. Okay. So that means this is the red. Okay. Coming back up here, on this side I only have a plus 2. If it's oxidation, it means it loses electrons, so the electrons should be added to the products. Things we lose come out. Are we okay with that? In order to make a plus 7 equal a plus 2, we need to have 5 electrons, because that's 7 minus 5 equals 2. Thumbs up if you're okay with that so far. Okay. Then I'm going to come down and do the bottom part. The same process, just the electrons will be on the other side. So Bi is already balanced, so I just need to fix oxygen by adding water. This tells me the number of waters I need to add is 3, H2O. That makes how many H pluses? 6 H plus on the other side. That's a plus. All right, the elements are balanced, but now the charge is not. So the overall charge here is a plus 3, because this is the only one. The charge here, I have -1 plus 6, so that's a positive 5. So those do not equal, so I need to add 2 electrons. Okay? Because if I add 2 minuses, it's really 5 minus 2, which now equals 3. Okay. Thumbs up if you're okay with that part. All right. The next step, I have 5 electrons on one and 2 on the other. That doesn't work. They must be equal. So the next part is to distribute a 2 to the 5 and a 5 to the 2. Are we okay with that? So that's where those lower numbers came in earlier. So I had 2 times 4, which was 8, 2 times 1, which was 2, 2 times 1, which was 2, 2 times 8, which is 16, and 2 times 5, which is 10. Okay? And those numbers go with the respective thing that's right above it. Then 5 times 2 is 10 electrons. 5 times 6 is 30 H plus. Uh-oh, don't do this to me. 5 times 1 is 5. 5 times 1 is 5. 5 times 3 is 15. You okay with that? Now I just total these up, but I'm going to cancel some things out first. Water's here on the top left. I have 8 of them here and 15 of them here. So I can reduce, right? The smaller number, that's just gone. And then 15 minus 8 left what number? 7 H2Os. You okay with this so far? I know it's ugly the way it's written, but like it sort of makes sense. All right, the 10 electrons, you can cancel those right off the bat because we made it do that, so we know they're gone. So the only other thing usually is just H plus. I have 30 of them on the left, and that's a big number and could give you a heart attack, but it doesn't matter. It can be a huge number. All right, so you have 30 on the left. You have 16 on the right, so the smaller number is just gone, and you subtract it from the big number, and that left 14 of these. And then there was nothing left to reduce. So then everything left you just write. So I have 2Mn plus 2 plus 5 BiO3 minus, and I guess I should have put the 14, but whatever, 14 H plus, and that's everything on the left, correct? Okay, this I should have crossed out a little bit more because it still looked like an 8. Okay, then I write everything on the right, 2MnO4 negative 1, all right, plus 5 Bi plus 3, plus 7 waters are still left. And that is my answer. Hopefully that matches what we did before. And it was a blast. It only took us 14 minutes. All right. It looks not super hard, so give it your best shot. All right, so the overall answer I got was 8. Oh my gosh, why does this button suck? Thank you. 8H2O plus 2P plus 5Cu plus 2. The order doesn't matter if you did it in a different order at all. It's fine. 5Cu plus 2H2PO4 minus plus 12H plus. Who had that right? So that was just a dumb math mistake. I hate those. I do it all the time, so I get it. Okay. So one more time, raise your hands if you had that. Okay. So that's under half. And that's actually pretty good. Yay. All right. Let's add a little sliver that's really not that bad, so don't panic. All of these assumed this was happening in an acidic solution where there was excess H+. But that isn't always true. Sometimes it happens in a basic solution, and in a basic solution, there's not H+, there's OH-. So when you do it in a base, you have to do one other thing. So if a reaction occurs in a basic solution, one can balance it as if it occurs in an acid. Once the equation is balanced, add OH- to each side to neutralize the H+ in the equation and create water in its place. If this produces water on both sides, you might add water from each side. So we come back here, we would say, okay, we're done. But this is in a base. So you have 12 hydroxides that you need to add to both sides. Okay? So I add 12 OH- to this side, and I add 12 OH- to this side. Now, this is going to stay 12 OH-, but this one makes 12 waters. But we already had 8 here. You with me? So the smaller number disappears, and to make this prettier, I'm going to just erase it and move this piece up. Okay, this is not working right today. I'm about to be angry. Wow, why is he so mad? Okay, I'm going to be mad because this is ridiculous. 12, oh my swear words. It's the same button. I'm pushing it over and over and over. You can hear me clicking the dang button. Okay, make sure I don't push the erase button again. All right, 12. Oh my goodness. Okay, this is gone. And then I subtract 8 from this side, right? Yep. And so now I really had 4 H2O. She's being a brat. All right. Okay. Does that sort of make sense? So if it's in a base, you add hydroxide to cancel it out, fix the waters, and go from there. Okay, so this is the one before. Okay, so this was it. This was when it was done. I'm going to add some red here. So let's pretend now it happens in a basic solution. So we just finish it. There's 14 H pluses. So I'm going to convert these just to 14 waters. Are you okay with that? And that means I added 14 OH- on this side. Okay? So now I adjust. The smaller of the two numbers cancels. So the 7 waters on the right cancels out. And I subtract 7 from 14. So I have 7 H2O left. And then I have just this plus 14 OH-. You okay with that? Okay. That's how you do it if it's basic. Now, I'm sure I have one. Oh, well, it's the same thing. All right. So ClO2 goes to ClO2 minus plus ClO3 minus in a basic solution. Okay. This one's tricky. Hold on. All right, it's the last one left, so you got it. we'll see. Chlorine's going to be oxidized and reduced in this same problem. Yeah, it's not as awful as it looks, but yes, it's tricky. Yeah, here, I'll give you the charges. This one's a -4, or +4, sorry, right? Because 2 times -2 would be -4. This equals 0. You all right with that? Okay, ClO2 minus. Now this one's a +3. And ClO3 minus, now it's a +5. So you'll notice one chlorine becomes more negative and the other chlorine becomes more positive. And is that possible? Sure. There's no reason that can't be done. Okay, you try the rest now. Goes to ClO2 minus plus ClO3 minus plus H2O. All in I agree there.
But it's not balanced.
How, it's not balanced? Okay. Now, the good news about a voltaic cell is it's really pretty easy. It's just a battery. It's a fancy name for a battery. All right, so in spontaneous oxidation reduction reactions, electrons are transferred and energy is released. Okay? So like if I have, just what this is copper 2 sulfate and zinc, it says right there. So you have a solution of CuSO4. You drop in a piece of zinc, and a reaction happens where you end up with ZnSO4 plus Cu. So we have Cu going from a +2 to a 0. We have zinc going from a 0 to a +2. All right? So an electron was literally moved from one place to the other. You okay with that? So when it happens in here, big deal. It just happens. But what we can do is we can separate these things and make the electron flow from one place to the other. And if we can make it flow in a direction we want it to, then we can use the flowing of the electrons for electricity, or we can use it to do work. So a voltaic cell is taking advantage of an oxidation reduction reaction to use what we call the electrical potential to do what we call work. Now, no one likes saying electrical potential is used to do work, so we just call it electricity. You okay with that? So this is just the study of electricity being produced, which isn't produced, I guess, but whatever, through a chemical reaction. Okay. We can use that energy to do work. I just said that, so we call this a voltaic cell. All right, we'll stop there because there's literally 16 seconds left.